students. Welcome to today's lab. Today we're going to be learning more about how optics and optical instruments can affect light rays, specifically working with lenses and mirrors today. There's two different types of lenses, converging and diverging, and the purpose of a lens is to allow light to travel through the lens and bend the light as it goes through. These two different types of lenses bend light differently. A converging lens generally has a shape that bows outwards from the center, shown here in the blue, and it can also be illustrated by an arrow pointing outwards at both ends. Converging lenses converge light. They take light that is coming in from separate angles and focuses it to a point. And in this way we can use them to make light more focused. The other lens is a diverging lens, shown by an arrow with the ends pointing inwards, and this picture here where the outsides bow inwards. And this does the exact opposite. Any light coming inwards from the left to the right will be deflected outwards, as shown by this picture here. Now, if you follow the rules that we learned last week for how light bends when it goes through glass, you could build these mirrors yourself, or just work with ones that can be bought quite easily that have already had all of their properties mapped out. So the important properties for these lenses are the focal points. The focal point is just a point where any light coming straight in from a very far away source or from a laser that is oriented at 90 degrees from the vertical plane of your lens will be reflected or refracted right to that point. So that is the point that light will be refracted to. The distance from the very center of the lens to that point is our focal length. However, not all light comes in at perfectly straight or perfectly parallel angles. So lenses can be used to focus light to points that aren't always the focus point. And today much of our lab will be involving how to find where these points are focused to. And what we're going to call those points are our objects and our images. So on this picture here, we have an object. The object is the thing that does the shining. So what I've drawn is a lollipop. You can imagine it as a lamp. Basically it shines in all directions, but we really only care about the light that shines through our lens. So any of the light going off to the left or above our lens, we don't really care about, even though this light actually exists. Also, our lamp here, it could be part of a larger picture. So if we had, say, a television here, each individual pixel would be represented by one of these little lamps. But to keep it simple, we're going to work with a single lamp. This lamp is a certain distance tall off of the center axis, so the very center of our lens. 90 degrees from that is the center axis of our lens, and we're making our height measurements off of that. We also know where our focal point is, just from the properties of the lenses. We'll work on finding focal points today, as well as using focal points that are given just from the lens manufacturer. And then the other known is how far from the vertical center line of our lens our image or our object actually is. And this is usually given by S1, or the distance 1, or it could also be the distance O, the object distance from the lens. The next part is to draw 3 separate ray diagrams, ray lines. So this works really well with lasers. We can actually point the laser to the lens and see which way that one ray of light would deflect. However, this also works for things that are not laser light, anything that shines normally or anything that light hits and you can see from the reflected light off of it. Again, these rays are going in all directions, but by drawing these 3 lines, we can figure out where the image will actually appear, where we will be able to observe a coherent or a good picture of our objects. So the first line we draw is completely parallel to this horizontal plane here, starting from the head of our lamp, or where the light is emanating. This goes perfectly parallel to the horizontal axis until it hits the lens center, And then, like I said before, any light that moves parallel to this axis that goes through our converging lens will be reflected directly to the focal point, refracted directly to the focal point. It doesn't stop there though, it continues on throughout space until at some point it hits something that absorbs this light. In our case, this is the observer here, located some distance off to the right, observing all the light rays that are refracted by our lens. The second ray that we're going to draw is the easiest. This ray is the same for pretty much everything where we're going to draw where the light goes through our optic. It goes straight through the very center where the vertical and the horizontal axes meet, and this means that it is unrefracted. So it continues to go on perfectly straight from the point that it left off into space this direction. And then the third line goes through the focal point on the near side of the lens, and then when it hits the center of the lens, it is refracted horizontally off in the continuing direction. So these two rays, the top one and the bottom one, they're basically images of one another. So if we looked at this backwards, we would have this first ray is basically represented by this ray here, going that way and then refracted upwards. And this ray here goes through the focal point and then it would be refracted horizontally. Where all three of these meet is where our image would form. So your eyeball, if it were over here, your eyeball would collect these three light rays coming off, and then your eye would extrapolate from that backwards to where the image actually forms, or where your eye sees this to be. And that is right here. So again, we're measuring from the horizontal axis downwards to get the height of this image. And since it is a downwards image, it's upside down, it would be an inverted image that shows up upside down, and it would be marked as a negative if we're measuring the magnification of these things. Which brings me to this part here. There are a few different ways to measure magnification. If you know the distance from the lens to your image, so S2 or S image, you can plug it into this equation here where your magnification, how many times bigger your image is than your object, you can plug that into here. If you know the focal length and the original object position on the left side of the lens, you can use this equation here. Or if you just have the sizes of the object and image, you can use this here, remembering that upside down images are negative. So that is the converging lens. It takes light that is originally spreading outwards and propagating through space, and it converges it to a point. After that point, the light continues onwards through space. The next type of lens we'll be working with is the diverging lens. This does the exact opposite. Light comes from one point. It is originally diverging, but the lens makes it diverge much faster, so it bends the light outwards away from one another. Again, we have our object here, mislabeled again, but that is the object. And then at some other point, we're going to create an image from it. This one's a little bit harder. Again, our observer is over here on the opposite side of the lens. This time, we're only going to draw two light rays, and they're the same light rays. This one here is exactly the same through the very center. It remains unrefracted. It's a straight line. It continues onwards. The other one we're going to draw is parallel to the horizontal axis. When that gets to the center of the lens, it now diverges outwards, and you can find the angle at which it diverges is by back tracing the line to the focus point. So from the center of there to the focus point, back trace that, and now you know which direction your ray is diverging outwards from. So again, your observer is out here. The observer's eyes would catch both of these rays, and your eye would extrapolate backwards from that to where the image actually is. Again, that is your image. There are a few things we can draw from this image. So this ray here, light actually passes through the point where we see our image formed. But this ray here, light doesn't actually travel through that point. Light appears to be traveling from that point because our eye backtraces that ray of light to this point, even though no light actually emanated from that point. So this is what we would call a virtual image. Virtual images basically mean no light is actually coming from that area, but your eye thinks it is. Your eye traces these rays backwards through the lens to a point where the light is not actually coming from, but the rays seem to be coming from. This height is also shorter than this height here, so our magnification would be a very small number for this. So by moving these objects around, we can get different types of images and objects and magnifications, and also by changing the focus points. So it'll be an exercise for the student. What would happen if the object were here between the focus point and the lens, or if it were over here between the focus point and the lens. One more equation you can use is if you know the distance from the lens to the image and the object, or 1 and 2, you can find the focus point. If you know the focal length and the original distance, you can find the second distance. And for some reason, if you know the second distance and the focal point, you could find the original distance as well. Alright, so the second part of this lab deals with mirrored optics. And mirrors work much the same way that lenses work, with the one obvious example that all of the light stays on the side it started on. When we draw mirrors, oftentimes it's a flat line with some sort of hatching behind it to let you know which side is the reflective side. So the flat side here is the reflective side. In your handout it looks a little bit different, but basically if the light starts on one side, it will hit the mirror and stay on that side. There are two different types of mirrors: concave here, where the cavity points towards the incoming light, and convex, where the cavity points away from the incoming light. And mirrors and optics like this tend to be part of a very large circle, or we can at least approximate them that way. And if we know the radius of this circle, we can then find the focal length from that radius. Depending on what type of mirror we're using, there might be a positive or a negative focal length that we're working with. And this equation here, very similar to what we used for the lenses, just the object image, or the object distance from the mirror, the image distance from the mirror, and the focal length are related in this way. The positive, negative values are related to you in your handout for working through the math. There's one example where if the object is much further away than our image would be, or much larger than our focal length, we can now approximate this to infinity. 1 over infinity is 0, and then we can arrive at this approximation here. So 1 over the focal length is about 1 over the image distance. So the light coming in from very far away with an object that's very far away will be reflected to the focal point. This comes in very handy when we're making telescopes and other things to look at super far away objects, because unlike with most objects, by the time the light from, say, a star reaches us, all of the light that is not basically parallel has gone somewhere else. It's missed the Earth completely. All the light from a star that hits the Earth is pretty much parallel. And we see this in our laser demonstration, but we need to create parallel rays of light using a laser. Starlight, sunlight, moonlight, even far away buildings and other things have this property. So in general, if your object is 2 orders of magnitude or 100 times further away or 100 times larger than your focal length, then you can make this approximation. So if we look at things out the window using focal lengths of a few centimeters, that's more than enough to use this approximation. And this works with lenses as well as with mirrors. So telescopes, whether they're refracting or reflecting telescopes, work off of this principle. So onto our ray diagrams. Again, we can find out where our images will be by drawing these ray diagrams in a somewhat accurate picture, starting with a concave mirror, which corresponds quite well to a converging lens. We have, again, our object. Imagine it's a lamp with light emanating from the top. The first line we draw, again, is parallel to the horizontal axis. When it hits the mirror, it reflects off, and this reflection goes through the focal point and then continues on in from the direction it came from. The second line we'll draw, and it should be the only other line we need for this, is through the focal point, and when that hits the mirror, it continues back in the direction it came, again, parallel to the horizontal axis. So these two lines, basically, if this were your image, this would be, or if this were your object, this would be your image, and if this is your object, this is your image. You would just need to change the directions that these lights come from, or that the lights are traveling. So again, we have an image where these two rays meet. This image is upside down, so it would be a negative height if we're looking for the magnification. This one would be slightly taller than this one, but it would be upside down. Our observer here sees these two rays of light coming out. Your eye backtracks to where they meet, and that is where your brain would put together the upside down or inverted image of this original object being reflected off of this mirror. And again, because there are actual rays of light hitting there, we would call that a real image. All right, and then convex mirrors are very similar to diverging lenses, except again, all of the light will stay on the side it starts on. So the light starts over here on the left from our lamp with its original height. Our lamp is the object. This time, the two rays we will create, again, the first one is just that straight ray parallel to the horizontal axis here. It hits the mirror and it reflects off in this direction. You can find that direction by connecting the focal length on the right side of the mirror, on the dark side of the mirror, to where the light hits the mirror, and then extending that up this way. The second ray that we need to draw for this setup is a bit more complicated. It's starting from the lamp here, and it's connected to the focal point on the horizontal axis of the dark side of the mirror. When this ray hits the mirror, this ray will reflect backwards, again, parallel to the horizontal axis. And if you're looking for this focal length here, if you know the focal length on the bright side of the mirror, it'll be the same distance from the center point of the mirror off that direction. So what we have now are two rays coming back towards our observer. This ray here parallel to the horizontal axis, and then this ray here extending upwards. Your eye will trace these rays back. Again, your eye treats all light as if it travels always in straight lines. So these rays coming outwards, your eye doesn't know that there's a mirror to stop them. It just continues backwards, back tracing these lines. And the same one with this one up here. Where these two meet is right here. We can see that our image there is erect or upright, and it is a bit shorter than our object. So our magnification would be smaller, but it would still be positive. And then another note about this image here is that it's a virtual image, because we know that it appears on the dark side of the mirror where no light could actually be hitting our eyes from. So since it is not created by actual rays of light, it's just our eye tracing the rays backwards, it is a virtual image. And we can find the two distances and compare them, the distance from the object to the mirror and the image to the mirror. And those are the measurements we'll be making. All right, so for a more straightforward demonstration of what's going on, we have our laser box set up, shining lasers straight outwards, and again, each of these lasers can represent some light reflecting off a surface. So when sunlight hits a surface, light reflects off of every bit that's the reflected light that your eyes actually see. Lasers are just a very good tool to use in the lab because they shine perfectly straight until they interact with something. So when we put a lens in the path of this light, we'll see how the light actually bends. The fact that all of this light is coming in one parallel direction means that the point where all this light is refracted to is the focal length of this lens. So all this light comes directly to the focal length. We can change to a different lens with a different focal length and see how that changes. Again, we have a different focal length there, so the light focuses this to a different spot, and then a third focal length. So these have all been converging lenses with different focal lengths at this point. Light comes in perfectly parallel, it gets refracted to one point, and then it continues on. A diverging lens, again, diverges the light. So light comes in parallel, and then it begins spreading outwards more and more after it leaves the lens. And if we wanted to make a system of more than one of these, we could put them together. So we have our converging lens. We could put another converging lens in there. It changes the light path a little bit. And then we could even put a diverging lens, or we could put that in here. The way you would work through this is basically to figure out where the image from the first lens is, and then use that image as the object for the next lens, and then use the image from that second lens as the object for the third lens, and so on. And doing this, you can really work your way through any number of lenses in a row. So the image from one lens acts as the object for the next lens. And keeping in mind that diverging lenses and some other systems can have objects that are not exactly where you would expect them to be reasonably, just reasoning through it without doing the math. Moving on to the next part, we have mirrors, and we learned last week that mirrors reflect light back in the direction that they came from. So no light will go through to the right side of this system. All of the light is reflected back, and the angle that the light hits with respect to the normal of the surface is the angle that light is going to be reflected backwards. So most mirrored optics are built to be a large radius or to have some uniform radius. And this radius is related to the focal length. So again, light coming in parallel is reflected backwards to the focal point. It works just like a lens, except all of the light stays on the side it starts on. So that was a concave mirror. A convex mirror does the exact opposite. So it's very similar to the diverging lens, except again, the light stays on the side it started on. So this mirror has a radius, but this radius goes to the right. All right, so what we have here is a far away image. Basically anything outside the windows counts as a far away image. And what we're gonna do is create an image on this screen here. And we'll know it's in focus basically when we can see the most amount of detail. And this is not a perfect process, which is why you don't want to use it to make fully scientific measurements, but it is a very quick and easy process to get you in the right ballpark. So you can see the inverted images of the trees showing up on the screen, and at some point they will appear to be the most in focus. So I think right about there, and I'm just moving the mirror back and forth, and I think right about there. So measuring from the mirror to the screen, whatever that distance is going to be our focal length. And for this one, it's about 22.5 centimeters. And we'll do this again off camera to get the numbers for the handout. All right, so now we have method 2 for finding the focal length of the spherical mirror. What we have is a lamp set up. This lamp has several graduations on it, so you can tell which way's up and how big your image is, and then a sheet to reflect our light onto. So we have our mirror again set up over here, and the basics of this is we are going to move our mirror so that our image, or our object and our image, will be the same distance from the mirror, and then we'll plug that into the equation, specifically equation 2.2 from the handout, and use that to find the focal length. So what we'll actually be finding is the radius of the mirror at this point. So we'll turn off the lights so we can see our image appear, and then some fine adjustments moving the mirror back and forth until we get the sharpest image possible. All right, yeah, somewhere in there. And we have our table set up so that the object is at 0. There's a ruler here so we can measure this. 44.5 centimeters. And then we'll do the second measurement off camera, but it would be the same method. All right, so now working on the focal length and magnification. What we have is our mirror set up at 50 centimeters on our track with, again, the object represented by this lamp at 0 centimeters. What we're going to do is start with our card here and then move the card to actually bring our image into focus. So we'll see it get clear, and then at a certain point it will begin to get less clear. So going back and doing fine tuning, we can find the point where our object appears to be in focus the best. So somewhere right around here. And now what we're going to measure is the distance between the card and the mirror. That is our image distance. We measured that to be 49 centimeters. And the next measurement to make is the size of our image on the card. So again, we did this before, but just from one side to the other. It doesn't really matter if we're working vertically or horizontally, as long as we are getting some sort of changing dimension. So measuring this we got 3 centimeters. And then the last measurement we need to make is on the object itself. So just the width of this object, and we got this to be 4 centimeters. So we're going to repeat this process with our mirror at 100 centimeters and at 30 centimeters from the lamp. Fill in the image distance, image size, and the object size will always be 4 centimeters. And then the students will need to find from those numbers the focal length, and then the magnification 2 different ways. All right, so for demonstration purposes, we have a different mirror. This mirror has a focal length of about 1 meter. And you'll see what happens first when the bear is placed closer to the mirror than its focal length, which is what we're seeing right now. And then as the bear moves away, what happens? Specifically, what happens with regards to the image? Is it inverted? Is it erect or upright? And is the image real or virtual? So you should have seen a switch happen at some point between some of those variables that are observable, and then you will need to think or read or draw your ray diagrams to figure out if it is a real or virtual image. We'll also Alright, so that last mirror was the concave mirror. This is the convex mirror. Observe the same observables. What changes? What happens? Is your image upright? Is it inverted? Is it real or virtual? And what changes as the bear moves away from the mirror? Alright, so now we're moving on to lenses. To find the focal length of the lenses by the method 1, the quick and dirty method, basically we want our screen with a light source on the opposite side of the lens, and we're moving our lens to where we get the sharpest or the most clear image. And then again, measuring the distance between the image on the screen and the lens itself. So measuring this before, we got about 8.75 centimeters. And we'll repeat this measurement again for the worksheet. Alright, so now we're set up for method 2. What we have is the same lens we were using to look out the window. We already know that its focal length is around 9 centimeters. The lamp is still at 0. And then our screen is down there, and we're going to move the screen until we get the sharpest image on the screen. So as the image comes into focus, we can, just go back a bit. Alright, so right about there, and now we know our distance from the object to the lens and our distance from the image to the lens. Then we will also measure the magnification of our image with the object having the same size. So this is the height of the image measurement here. All of these will show up on the handout you get. And then we're going to repeat this where the lens is moved. Right now it's at 2 times the focal length. We'll move it to 2.5 times the focal length, and then we'll move it to 3 times the focal length. And these numbers will appear on your handout. So from these numbers, you are to calculate the focal length and the magnification for this lens. Alright, so now we're using the same lens, and as we start closer than the focal distance, make your observations here for if the image is inverted or erect, or if it is virtual and or a real image. This is again closer than the focal distance, and as we move away, notice how these things change. So now we're at a distance greater than the focal distance. How does the image look? Upright or inverted? And is this image real or virtual? And make sure to fill that in. Alright, 252 students. The last part is how to measure and use a diverging lens in our setup. And on its own, a diverging lens is very hard to actually measure the focal length of, so what we're doing is setting up several lenses in a row to find out how to actually use and find the focal length of this diverging lens. So first we have our converging lens, which we've been using. It's placed about 2 focal lengths away from our object here. And now we're just going to move the screen to find the focal length where the image is in focus. And what we're going for here is a 1-to-1 ratio, so the object and the image should be about the same size as long as our lens is placed here. So we will make this measurement here, and it's just about 4 centimeters, 4.25 to be exact. And then we're also going to measure from the lens to our object, and that is 19 centimeters. That is on your handout sheet that you'll get. The object size, again, stays at 4. So now what we're going to do is add in our diverging lens somewhere in the middle, and the instructions say to rough out the image in focus. So we're going to be moving both the screen and the diverging lens, basically so the image formed by our converging lens becomes the object of our diverging lens at the focal point, so that a coherent image actually forms on the screen. So we'll just move both of these until we get a pretty clear image. So somewhere in, and you can see that coherent images form at lots of places, so we're going to go with the one that gave us the magnification we're looking for, that we've actually measured. So somewhere right around there. All right, and these measurements are on the handout. So our image size here is 8 centimeters, so about twice as big as our original object. And then the distance, 7.4 centimeters from the diverging lens to the image, and then our lens to lens difference is about 15.6 centimeters. So this is what data you need to complete the first 1-to-1 column of this table. The bottom 2 rows, as well as the average, are left for the student to come to a conclusion on. And then for the next 2 columns, that data will also be given. But basically what we're trying to do is set up this situation here, where just from the converging lens, our image is about half, or about 3/4 of the size, and then about half the size of the original image, and then work from that point.